An AI agent downloads a code formatter from the internet. Would you rather give that formatter an entire Linux container or a tiny sandbox that begins with access to absolutely nothing? That is where WebAssembly becomes extremely interesting, but it is also where the headline "WebAssembly will kill Docker" begins to fall apart. WebAssembly and containers do overlap. Both can package code, isolate execution, and move workloads between machines. But they package different things. A container packages an isolated process with the files and dependencies it needs. Containers on the same machine share the host kernel. This is powerful because existing server software already expects operating system features, file stills, networks, package managers, and long-running processes. A WebAssembly module is closer to a portable program format. The WebAssembly 3.0 specification describes a safe, compact, hardware-independent, low-level code format. It can be decoded, validated, and compiled efficiently. And despite the name, the core format does not depend on a web browser. The key difference is authority. Core WebAssembly code has no ambient access to the host environment. It cannot simply reach into your file system or open a network connection because it feels like it. The host must provide imported functions that make those operations possible. WASI, the WebAssembly system interface, standardizes many of those host capabilities. Files, clocks, randomness, networking, and other operating system-like services. A WASI application begins with no ambient authority and receives only what the host grants. For an AI agent, that is a beautiful security shape. Suppose the agent needs a formatter. The runtime can grant read access to one temporary input file and write access to one output directory. No home folder, no SSH keys, no random network access, no package manager scripts. The formatter gets the minimum world it needs. The same model works for image conversion, document parsing, code analysis, policy checks, and user-provided plugins. Small tool, small capability set, short lifetime. This is where Wasm can beat a container operationally. The artifact can be compact, startup can be fast. The runtime can embed directly inside a larger application. Different source languages can target the same portable execution layer. And the capability boundary can be expressed around the individual tool. Now try the same argument with a complete product. Your application has a web frontend, a Python API, PostgreSQL, a queue, native image libraries, background workers, persistent volumes, health checks, and an operations team already using container registries and Kubernetes. WebAssembly does not make that world disappear. The database expects durable storage and mature networking. The Python service may depend on native packages. The operations platform understands container images, logs, probes, secrets, volumes, and rolling updates. Recompiling pieces to Wasm can be possible without being the cheapest engineering decision. This is why Wasm starts faster is not enough. Startup matters most for short-lived functions, plugins, edge workloads, and bursty tasks. A database running for 30 days does not care that its process took a few hundred extra milliseconds to begin. It cares about durability, tooling, recovery, and operational trust. Isolation also needs careful language. WebAssembly's memory model and capability design create a strong sandbox foundation. They do not make every module harmless. A program written in an unsafe language can still corrupt its own internal memory layout. A malicious module can exploit a vulnerable host function. Hardware side channels still exist. And if the host grants the entire file system, the capability model cannot save you from the policy you chose. Containers are not magical security boundaries either. They share a kernel, and configuration mistakes can expose far more than intended. Both systems require patching, least privilege, resource limits, and a clear threat model. So use a workload test, not a technology slogan. Choose WebAssembly when the unit is a function, plugin, extension, user-supplied tool, policy module, edge computation, or agent capability. It is especially attractive when startup, portability, language interoperability, and narrow host permissions matter. Choose a container when the unit is an existing service, database, complex runtime, or application with operating system dependencies. Containers win when the deployment ecosystem, debugging workflow, network model, and operations. Tooling matter more than the smallest possible sandbox. Choose both when the product contains both kinds of work. This hybrid is probably the most useful architecture for AI systems. Run the main agent service in a container. It gets a known environment, normal observability network configuration, and deployment tooling. Run untrusted or variable tools as WebAssembly components inside a capability-controlled runtime. The container owns the service boundary. Wasm owns the plugin boundary. Now, a downloaded formatter does not inherit the authority of the entire agent service. A customer-provided function can run with a time limit and a tiny file system view. A parser written in another language can expose a typed component interface without becoming another network microservice. The boundary can also improve failure recovery. A short-lived component can be given a memory ceiling, fuel, or execution limit, and a disposable output directory. If it fails, the host discards that instance without restarting the complete agent service. The important point is not that every runtime exposes identical controls. It is that the tool is designed as a replaceable capability instead of an all-powerful child process. That does not kill Docker. It removes Docker from jobs where a complete container was too large a unit. WebAssembly 3.0 strengthens the core standard, while WASI and the component model continue building the world around non-browser applications. Runtimes such as Wasm time already support command line and embedded execution. The direction is real, but ecosystem maturity is workload specific. Language support, debugging, native libraries, interfaces, and runtime behavior still vary. A clean demo with one compiled function does not prove that your production stack should be rewritten. So ask 4 questions. First, what is the smallest unit I need to isolate? Second, which exact capabilities does it require? Third, how long does it live? Fourth, which operational system must support it after the demo? If the answer is a tiny tool with 3 explicit permissions and a life measured in milliseconds, WebAssembly deserves serious attention. If the answer is a stateful service with mature dependencies and a team already operating containers, Docker is not being killed. It is doing a different job. The future is not one box replacing another. It is choosing a smaller box around risk. Containers package complete services. WebAssembly packages portable capabilities. For AI agents, that second boundary may become essential. The winning architecture will use each one where its isolation unit matches the real workload.